Hey folks, this is the answer to number 3 in the homework, which is the Michelson problem where he's shining light from an octagonal mirror that is rotating this way, bouncing it from one mountain to another 35 kilometers away. Alright, and we want to know how fast does it need to rotate, alright, in order such that when the light first hits this mirror, in the time it takes to travel the 35 kilometers there and travel the 35 kilometers back, the mirror would have moved 1/8 of a turn, because basically that's the shortest amount of time. I mean, you could do this for not just 1/8, but also 2/8 and so on, you know, with faster speeds. But the slowest speed would be the time it takes for when the light hits here, goes out and comes back, that this side of the mirror shifts to this side of the mirror and is in the perfect location to bounce that light into the observer's eye on the other side. So that's 1/8 of a turn because we're using an octagonal mirror in this case. All right, so we have, all right, 35 kilometers of distance that the light is traveling, but of course, all right, it's 35 kilometers there and 35 back, so we have to multiply by 2 to get 70 kilometers, and of course we're in kilometers and we should definitely turn that into meters for the sake of our math, so our total distance is going to end up being 70,000 meters of distance. All right. We also know we're using c, the value for c in this case in particular, we are using 3 times 10 to the 8th meters per second. So in our equation, our simple equation of velocity equals distance over time, all right, if we rearrange this, all right, we well, actually, yeah, we don't need to rearrange it right now. We can just plug in our stuff and say 3 times 10 to the 8th meters per second is going to be equal to 70,000 meters divided by some kind of time, all right? And that time is going to be the time it takes for this 1/8 of a rotation. So if I solve for t here, I should get 2.33 times 10 to the -4th seconds, a very, very fast, you know, a very short amount of time, telling us that in 1/8 of a rotation, it takes that amount of time to do that. So if we want an actual answer in terms of revolutions per second, all right, we already know that 1/8 of a revolution takes 2.33 times 10 to the -4th seconds to complete. So if I take 1/8 divided by this, I will get our actual ratio of revolutions per second. If 1/8 revolution takes that amount of time, 1 revolution, all right, should take, you know, this amount of time. So if you do this math, 1/8 divided by 2.33 times 10 to the -4th, you should get an answer of 536 revolutions per second, which is insanely fast. I mean, that's wicked fast. But, I mean, we're only using 2 mountaintops that are 35 kilometers away. If you think of the other experiments that we were doing, you know, Romer used literally the distance from, the Earth on one side of its orbit to the other side of the orbit. So that's a huge amount of distance. For Fizeau, we were using 8,000 meters, all right? This one, you know, we're using 70,000 meters, which is farther than the Fizeau experiment, but still we're talking about terrestrial distances. So 536 revolutions per second for our octagonal-shaped mirror.